Hello, my name is Dale DuFay. I'm going to start this video off with a simple test. I'm going to compare this mechanical stopwatch that's calibrated for this reality to the cadence of my own personal stopwatch that I had perfected over my lifetime. In fact, it was I usually used to practice it out of boredom, or when thunderstorms were occurring, and I would time the flash from the lightning to the sound of the thunder to determine how far away the lightning strike was and things like that. And I practiced it well into my adulthood, and many times I just kind of almost caught myself doing it out of habit. And every time I checked it with the stopwatch of that reality, it was always like right on. In fact, every time I aired, it was usually my cadence was too fast, so I had to force myself to slow down every time, and I finally got it perfected over decades, So I'm actually really glad I did that because there is obviously a discrepancy with the stopwatches in this reality compared to the reality that we recall. So we'll do this simple comparison, and I used to always use the 1,000, 1,000. Again, I had to really practice it, get it slowed down, and still do it, because of the discrepancies. So let's do a quick comparison here. I won't even look at this mechanical stopwatch because I don't want it to influence me or make me slow down or speed up. But I'll try and do it in one breath and keep the cadence just right, like I used to always be able to do and still can do. So let's do it right now. Let's start. The second I start, I'll start my 1,000. 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. There we go. It's always right on, right within a few, milliseconds, split seconds. I mean, it's just always right around 15 seconds in this reality when I count to 10 seconds in the reality I recall, thanks to that cadence I perfected. So it helped me to realize that, obviously the time in these realities is a lot faster, 50% faster, but yet the time remains the same. It helped me to, understand that linear time is not as we always thought. So what is that telling us really besides, the linear time? The reason again I could say that because, you know, if that were true, then in this reality I'd be 90 years old because, that's obviously not the case. I'm the exact same age in every reality. So time is not linear at all. It's just something that we human beings invented. Our early attempts, of course, were done with sundials and still being used today, very accurate. But we have to look at where's the calibration come from on these sundials. Of course, that took a while with location and everything, and generations of observations and things like that. I like this clock here. It helps us to realize that our life is finite, and that's why we need time in the first place. It's our short-lived lives that caused us to invent time, and of course it has its benefits as far as timing things of throughout your everyday life and whatnot. But for the most part, time is irrelevant, and that was disappointing to me to find out because I've always loved stories about time, any sci-fi movies or anything. The time was always my favorite subject, time travel, things of that nature. So I was always very interested, but then to find out that it's really irrelevant for the most part, along with time and space. The Mandela Effect's proving that. The great teacher, the Mandela Effect. The reason we know space is irrelevant is because we have realities across the galaxy some 75,000 light years from this location, this reality. So the distance between is, you know, inconceivably vast. So it's irrelevant. But because our actions are identical for the most part and instantaneous. But this, so how can we, so why does this reality, why is this reality faster by 50%? The best explanation immediately is the size of the Earth. Well, is the smaller Earth spinning faster? No, not at all. We have to assume that they're all spinning at the exact same speed off their axis. And we can say this with confidence because the Milky Way galaxy rotates off the galactic center, say its, you know, its hub, if you will, at the exact same speed, regardless of where you are within the Milky Way galaxy. You could be at the tip or close to the galactic center, you're going the same speed. And that's not the case with Kepler's laws of dynamics with, like, say, a helicopter blade. The speeds vary considerably from hub to tip. So, but this is not the case with the Milky Way galaxy, so that gives us a hint, a clue, that the Earths do indeed spin at the exact same speed in every reality. And then if we go back to square one of where does time originate, it's from one full revolution of the Earth. One full revolution is a 24-hour day. And each reality, each Earth, regardless of what size it is calibrated to a 24-hour day. And that's very interesting and also helps explain why in this reality where the Earths are in some cases 4 times smaller than the realities some of us recall, you know, is exactly the same time. You know, that's what's really strange about it, is that each Earth is calibrated for that 24-hour. It makes sense. I mean, it's something we can easily overlook because it's so obvious, you know. And then it explains again why we have the variations. Because regardless of the size of the Earth, it's calibrated to a full revolution. So if the Earths are all spinning at the exact same speed off their axis in every reality, then it's going to take a lot longer for a larger Earth to complete that 24-hour full revolution. So that Earth was calibrated for one full revolution. Those super Earths, those matriarchs on the outer reaches, they're spinning at the same speed as these dwarf Earths, and they're taking much longer to make that one complete revolution. And these Earths here obviously are 50% faster. It's remarkable. And it explains why there's that difference. That's why there's a discrepancy with our own personal stopwatch and the calibrated stopwatch in this reality. It explains that. And then it also explains why we experience time differently throughout the day. Like when things are going real good, and you know, the time seems to go faster. And when things are going worse and bad, then the time is much slower. And it was always kind of mysterious as to why that would happen. But the fact, you know, knowing now, thanks to the great teacher, the Mandela Effect, showing us that we have different realities where the time varies considerably, upwards of 50% in some cases. It's remarkable. Of course, the time is identical as far as the calibrated time in a lot of these realities because the Earth is the same circumference. These Orion dwarfers are 24,800 miles in circumference. So therefore, in that case, those are Earths, all the Earths that size are going to complete the full 24-hour, or the full revolution, which is calibrated to 24 hours, divided in a 24-hour full revolution there by a day. So that helps explain a lot of things, not just what we're experiencing through our journey with the Mandela Effect, but also why we experience time differently so much, even sometimes within any daily event. It's fascinating. So many things are explained. You know, I personally always wondered about that, why we experience time differently throughout the day. And why would that be? How can we know, you know? It's just, again, it's like the crossing of the time zones. How would you know you're crossing time zones? Again, they're invented by human beings. They had to, for the railroad industry and having schedules just right. And that was developed over a great deal of time. But, you know, timing was also important for the mariners. And, you cross the oceans and you got to get your longitude and latitude. The timing is very important. And it's a lot of effort put into timepieces here. This is the first atomic clock. And look, I mean, there's a lot of mechanical things going on here. I mean, here's a more modern version of an atomic clock, and you could just see the great amount of detail and energy and effort it takes to keep that calibrated time precise. And it's true in every reality. Every reality has its atomic clock, but it's calibrated to that reality, that Earth size. This is a quantum atomic clock here. So they've come, you know, a long way from the sundial and hourglasses to these. You know, this is compact atomic clock that fits in satellites because the timing is very important. And of course, that's the importance of time in general, is for instruments like that, satellites and things like that. But for the most part, the Mandela Effect is showing us that time and space is irrelevant. And, you know, here's this, the only concept of time they have, and space, and, you know, the future and the past and the present. You know, that's basically the only explanation. And we know it's not linear now, and thanks to the Mandela Effect, and it gives us a better understanding. And in future videos, we'll go over subjects like time travel and things like that. Is time travel possible? Is the Mandela Effect showing us that? It gets pretty deep, and of course, as with everything, when it comes to the Mandela Effect, it's impossible to prove. So with that, I thank you for watching, and we'll talk at you later. Love you.